Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all of you. So today we are going to start a new subtopic that is 8.6.3 from the Potter textbook, which is the approximate solution to the laminar boundary layer. So what actually we need to determine, or we need to obtain from this part is actually to get the solution, approximate solution. So this is the using the VKMI for the laminar boundary layer. So before we go to the solution, we will need to define or to get the velocity profile related to this laminar boundary layer. Okay, but before we proceed with this, how we can obtain the velocity profile associated with this laminar boundary layer on a flat plate with a zero pressure gradient. Can you please complete this activity? It's just a definition. So we have delta, delta D, theta, the tau naught. Okay, in some book they call it tau W. Okay, the CF, the FD, the big C with the F, or also the CD. Can you give the definition? I mean, just state what is actually this, all this term means. Okay, you can refer to the textbook also, or from, if you can recall back what I have share with you in the past slide or past videos. Okay, so in order for us to get the approximate solution using the VKMI for this boundary layer, so we need to know the velocity profile. Okay, because we look because we know that theta is the characteristic length. So in the equation, the approximate solution, the von Karman momentum equation equal the theta, and the theta equal the small u. Okay, the velocity profile, okay, associated to the flow inside the boundary layer. So it can be either the flow is laminar or the balloon. So we can only solve using this approximate solution if we know the velocity profile. Okay, if we know the velocity profile. So that is why we need to determine this velocity profile. How we are going to determine the velocity profile? So we will start with the laminar boundary layer first. So we know that the von Karman equation is the approximate solution. So this is the equation. So we know that we got the theta here. So the theta is actually in the function of this equation. So normally the u infinity we don't have problem. It's just a constant value depending on the flow, the external flow or the uniform flow magnitude. But we need to know on this small u because we are going to do the integration, because this small u is a non-uniform flow. Can you define what is a non-uniform flow? Anybody can define what is actually a non-uniform flow? Okay, so because it's this is u. Okay, this non-uniform, so there must be a velocity profile related to the u. So how we are going to get the velocity profile? So they are in solving the velocity profile inside this laminar boundary layer. So we have these four boundary conditions. Okay, the boundary condition 1, 2, and 3. This is associated with the characteristic of the boundary layer, but for the boundary condition 4 is actually related to the Navier-Stokes equation. Okay, so what is actually we need to do? So for the 1, okay, we know that the u equal to 0 and the y equal to 0. Okay, we have here. This is the velocity at the wall. Okay, so this is actually what we call this condition, u equal to 0 and y equal to 0. Anybody can recall it back? What is actually the term here with the viscous effect? Yes, there's no slip condition. So this is the no slip condition here. Okay, so you can write this is the no slip condition. Okay, and we said that u equal to u infinity and y equal to the delta. Okay, because this is just 0.99, so you can approximate u equal to the u infinity and the y equal to delta. Okay, so that is the second boundary condition. Okay, and if you use this from here also, there will be no change of this velocity gradient at y equal to delta. Okay, we know that when the velocity is equal to the big U infinity, so there will be no change of the velocity gradient with the y. Okay, then there is no change of velocity with y, or the velocity gradient in the y is equal to 0. So that is the condition number 3 we should satisfy. Okay, and another one, the fourth condition. So this is actually from the Navier-Stokes. That is equation 5.3.14 from chapter 4. Okay, so at this equation y equal to 0, you can get everything 0. We don't have the pressure. We don't have this term also, this term also, this term also we can ignore. So actually we know that we just covering on the x component, so we don't have the y, we don't have the z. So this equation also will be equal to 0. So that is how we get y equal to 0 and y equal to 0, and this is actually the second derivation of the del square u over the del y square will be equal to 0. That is from the Navier-Stokes equation. Okay, that's all for this topic, for this part.